All right. Try the practice problem on your own. The solution is posted on Google Classroom. Next, we're going to look at the example. Now, this example has multiple masses, so we're going to do a little review of multiple masses first. So, multiple masses have a common force between them. This is going to be our third law pair. Now, because it's a third law pair, one of them is going to be positive, one's going to be negative, because they have opposite directions. There's also going to be a common acceleration, and we have a couple considerations here we have to keep track of. One, we need to make sure that they're both positive. Also, because we're going to be dealing with both rotational and linear accelerations, we're going to have a relationship between them that the linear acceleration is equal to the angular acceleration times the radius, and this radius is just a link for us between where is my linear object connected to my rotating object. All right, so let's take a look. So we have a disk, and if you'll recall from our table, a disk has a moment of inertia of 1/2 mr squared. And it is in a rotational situation where we have a mass hanging here and it's going to fall some distance h, it tells us. And we're trying to find the linear acceleration of this block. So this one's going to be in a linear situation. So for the rotational one, we're going to sum up the torques and set it equal to I alpha. For the linear one, we're going to sum up the forces and set it equal to MA. All right, we're still good. So, first thing we're going to want to do is make sure that the acceleration is in the positive direction for both. So this one is going to undergo an angular acceleration alpha in this direction, and so that is my positive direction. This one is going to experience a linear acceleration. This I'm just going to refer to as A tan. I'm just going to call it A though. So this is the positive direction here. Now, because I'm summing up torques and summing up forces, I need to draw some free body diagrams. So let's start there. So acting on M2, there's gravity, so M2G. There's also tension in the string pulling up. For my disk, I have tension pulling down on this edge. I also have gravity acting down from the center, but because I've chosen my axis of rotation, or the axis of rotation is at the center, that force from gravity won't produce any torques. Okay, so let's go over and generate our equations. Okay, and again, we're going to try and link the tangential acceleration with the rotational acceleration. So sum up the torques. So I have tension acting at a 90-degree angle from the radius. So I can just say tension times R. This is my positive direction. It's equal to I, because I have a disk, it's 1/2 times my mass, M1, times R squared times alpha. And then down here at the linear one, down is my positive direction. So I have M2G minus tension equals M2A. Now these are my two equations that I'm going to solve. And so we're looking for common variables. So I do have a common variable of tension. Notice one is positive, one is negative. Opposite and equal, third law pair. But here I have linear acceleration. Up here I have rotational acceleration or angular acceleration. So what I'm going to do is I'm always going to want to substitute in for alpha, even if I'm solving for it using this equation. And you'll see why in just a second here. So since my string is connected at a distance r, the linear acceleration is going to be equal to alpha times r. So if I solve for alpha, I'll get linear acceleration divided by r. So let's go ahead and put that in. So I have tension times the radius equals 1/2 m1 r squared times alpha, which is my linear acceleration divided by my radius. Now you're seeing why I'm making that substitution, because this r gets rid of one of those r's. This r gets rid of the other one. And so I'm left with simply tension is equal to 1/2 m1a. Now I can go ahead and make a substitution, because now I know what tension is in terms of A. Plug it in here, and now I'm left with a single equation with a single unknown, because they did tell us what M2 and M1 were. So now I can go ahead and solve for A. Okay. Once I know the acceleration here, it turns into a 1D motion problem to figure out how fast it's going at the bottom. So just list your variables and choose an equation from the sideboard.